We're now going to introduce some important matrix operations and special matrices that we'll need in the fall class. The first is the transpose operator. Now, the transpose of a matrix, written A transpose, that's how I would read that. Of course, it's just a capital T as a superscript, is the matrix whose rows are the columns of A. So here I have a matrix A with 4 columns, and if I were to take the transpose of that matrix, I would get this matrix with 4 rows, each being a column of A. The transpose is useful for forming many meaningful matrix products, typically of the form A transpose A. We'll talk about matrices of this form when we get into the fall semester. The next is the identity matrix. The identity matrix, which is typically denoted I, again, a capital bold-faced I, is to matrix algebra what the number 1 is to scalar algebra, the multiplicative identity. So when we multiply a matrix or a vector by the identity, that matrix or vector remains unchanged. So for any matrix A, multiplying by the identity just yields the matrix A, and that is true whether I multiply by the identity on the right or the left. Now, these two identities that I have in these two equations might be of different size. If A is a rectangular matrix, meaning it has different number of rows and columns, so if A is m by n, in this instance, in this first equation, this identity must be n by n. And this identity must be m by m, where m is the number of rows, again, n is the number of columns, because we have to have the dimensions of the matrices line up in order to multiply them. What does it look like? Well, it's a matrix of all zeros with ones on the main diagonal. The main diagonal is what we call this longest diagonal of the matrix. We commonly specify the size of that identity matrix with a subscript. So I3 would be the 3 by 3 identity. IN would be the n by n identity. Although most often the size of the matrix is just assumed based on the context of the problem. Next, we have the inverse matrix. Now, the inverse of a matrix A, if it exists, is denoted as A to the minus 1. We read that as A inverse. And that's a matrix for which multiplication by A results in the identity matrix. Okay, so A times A inverse is equal to I, and similarly, if I multiply by the inverse on the left, I would also get the identity matrix. Now, it's important to realize that anytime you perform an operation that involves canceling terms, it must be done with an inverse matrix. For instance, if I have this equation here in linear algebra, ax equals lambda x, I can infer from this equation that A is a matrix because it's capital and bold-faced, x is a vector, it's also bold-faced but lowercase, and lambda is just a scalar number. It's not bold, and typically we use those Greek letters to be scalars. Now, I can't just cross out these x's in linear algebra. That doesn't have a meaning. We get used to performing operations like this in scalar algebra, but we're not actually, crossing something out is not a mathematical operation. What we would be doing is dividing by x if it were scalar algebra. But there's no such thing as division by a vector. That's not, there's no definition of that. Instead, we have to multiply by an inverse. And in this case, it's impossible for X to have an inverse because it's not a square matrix. Only a square matrix that is full rank, something we haven't talked about yet, but we will have an inverse. So in order to have an inverse, a matrix must be full rank and square, meaning same number of rows as columns.